Hello, welcome to today's webinar, Resilient PNT for a 5G World, brought to you by GPS World Magazine and our sponsor of the event, Orolia. Orolia is the world leader in resilient positioning, navigation, and timing solutions that improve the reliability, performance, and safety of critical, remote, and high-risk operations, even in GPS and Gnss denied environments. I'm Mackenzie Schoner from North Coast Media, content marketing producer for GPS World Magazine, and I will be the moderator for today's event. Before we get started, I want to let you know that today's webinar will be recorded. You are currently in a listen-only mode. A recording of this webinar will be posted to gpsworld.com/webinars and will also be emailed to you tomorrow. At this time, I would like to acquaint you with the ways you can participate during today's presentation. Please notice the Q&A panel at the left-hand side of your console. If you have a question, type it in the panel's text box, then click Submit to place your question in queue, or you can tweet using #GPSWorldWebinar. We encourage you to ask and enter any questions you may have for our speakers during the presentation. We will address these questions at the end of the presentation during the Q&A portion. Questions submitted during registration have already gone to our panelists and may be covered during today's presentation. If you experience any technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issues, and assistant producer Joseph Ciccolini or I will personally assist you. You may learn more about our speakers by viewing their photo, bio, and email address in the panel located on the upper left-hand side of your console. If you are logged into your social media accounts, you can share this webinar's title, description, and URL with your friends or colleagues using the Share This widget you'll see at the bottom of the screen. Finally, at the right side of your console, you will find a PDF of today's presentation slides, which you can download, and a link to visit both the GPS World and Orolia websites. I would now like to introduce you to today's presenters. Today we will be hearing from Cecil Taylor, Senior Product Manager for Anritsu Company. Cecil has been a telecommunications professional for more than a quarter of a century with a varied background in software development, product management, and marketing. We will also be hearing from Lisa Perdue, Product Line Director for Orolia. Lisa is a world-leading expert in testing critical GPS and GNSS systems and has trained hundreds of engineers and technicians who are responsible for high reliability positioning, navigation, and timing applications. Lastly, we will hear from Pierre Gerard, Senior Cybersecurity Expert with Thales. Pierre co-designed security solutions with customers and partners and is technology advisor at corporate level. At this time, we will be doing our first poll. You will have 15 seconds to answer the following question. How familiar are you / how likely are you to use high accuracy PTP timing, HAPTP, or White Rabbit? Please enter your answers now. We will now be going to the results. Interesting. All right, at this time, I will be passing over to Lisa Perdue, Product Line Director for Orolia. Lisa, take it away.
Hey, thanks, Mackenzie. And thank you everyone for joining me today for this webinar session. I wanted to get started by looking at the 5G infrastructure timing requirements, because they're really not that clear. It's not that easy to just Google what are the timing requirements and then find a definitive answer. They're hidden in all sorts of different standards. The two main ones are the 3GPP standards and the ITU-T, which is the Telecommunications Standardization Sector recommendations. There you'll find all the different requirements for the different parts and pieces of the entire 5G infrastructure. I also wanted to point out that time and phase sync are important for 5G, not just frequency. So if we were having systems that were timed by like sync E or just by frequency signals, now they need to integrate some timing signals as well. If you summarize down all of those different standards and all the different pieces and parts, the main requirement from the primary reference time clock, or what I'll call from now on the PRTC, to the radio unit is plus or minus 1.5 microseconds in total. And you can see that on the diagram at the bottom, which I found from Ericsson, where they showed the overview of the entire infrastructure and then the different timing requirements for the different pieces. So you can see there's an absolute timing requirement where the plus or minus 1.5 microseconds comes in, but there's also a requirement for relative synchronization within a cluster of radios. So timing plays an important role in the 5G infrastructure. We need to make sure that all of our elements are synchronized properly. Taking a look at the role of GNSS in 5G infrastructure, you can see that I've really done a general diagram here. There's many different configurations. There's many different places where you can place the GNSS-based PRTC along the infrastructure chain, but usually it's in the core or at the beginning of the chain where you'll have your PRTC, which is typically a PTP grandmaster, and it will contain some type of holdover oscillator, either a crystal oscillator or a Idm oscillator. We've also seen companies taking it a step further and having a cesium backup. So a cesium is a much more stable clock source that can be used as a backup in case of GNSS loss. So let me talk for a second about what holdover is. So when I'm talking about holdover, this is when there's a loss of the GNSS signal or the GNSS signal has been deemed not valid or no good to be used for this application. The unit will go into holdover where it no longer uses the GNSS signals, but it uses a backup clock, which is, like I said, either internal or could be external in the case of the cesium. That backup clock is going to provide stable timing in the event of loss of GNSS, but depending on the type of oscillator used, it's only good for a limited amount of time. So we need to make sure that we're using the right oscillators to cover any outages that might be expected. Because everything starts there with the GNSS and then that primary reference clock, we need to be aware of the different threats to GNSS, especially the ones to 5G infrastructure. So these are all the threats to GNSS, but there was a couple of them that I wanted to point out for this application, which can make things tricky. And the first one is spoofing. So this is the covert, or it's an actual attempt to deceive the receiver into thinking that its timing is different or its position is different. It's a way to deceive the receiver. But spoofing a fixed timing installation is relatively easy compared to spoofing a moving vehicle. So the fixed infrastructure is very vulnerable to time-based spoofing of GNSS. It's possible to pull the time off, for example, in a way that the receivers can't see as an error. So just your receiver itself will happily follow along if the spoofing signal, for instance, is pulling the time off 10 nanoseconds every second. Seems like such a small amount, but when we're working with that 1.5 microseconds, it doesn't take very long time to pull it off into an unusable state where it didn't even go into holdover because it didn't detect that there was a problem. So that's one of the main things that you'll see that I'll talk about here is the detection of the event. So it's good to have the backup systems, but if we don't know something's going wrong, if the system hasn't identified an issue, then it's continue to use GNSS even though the data may not be good, and that will disrupt the entire systems, everything downstream from it. Then the other one is interference. So with interference, it's easy to say when something is completely jammed, that the receiver or the primary reference clock will go into holdover. And that's true because it's seen as a loss of GPS. There's no usable data there. But it's also possible to have interference that's not high enough level to completely jam a receiver, but enough to disrupt its operation. So it might not really know that something's wrong. It might not go to holdover. It might continue to try to hold on to these very low-level signals, try to use them, but when doing so, it's actually outputting a solution that's worse than if we had been in holdover in the first place. So how do we protect against those kind of threats that I was just mentioning? The first thing that we want to do is start at the antenna level. So there's a couple different ways, a couple different antenna types that we can use. There are what we call horizon blocking antennas, and these are very good and very useful and very effective in fixed timing installations. So what we're doing with this type of antenna is not allowing any signals to come in below a certain elevation into the unit. So if your antenna is on top of a building or high up, it won't be receiving any signals based from the ground or reflections from the ground or interfering signals that are being generated maybe in another building nearby. If it's lower than where the antenna is installed, then we'll block those signals. We'll attenuate those signals so that they don't even get into the system in the first place. There's also the SERPA antennas, or controlled reception pattern antennas, that are widely used in the defense and military markets, but we're also starting to see them used in the commercial markets now too. So GPS Dome is one of them. It's really just a 2-element SERPA, but it can protect against and create a null in the direction of a jammer or interfering signal. So that again, we're protecting the system from that interference even getting into our systems. But the main thing that we want to do, if it is there, is we want to detect it. So that is, one of the very key things is that we have to know something's going wrong before we can do anything about it. So there's different options for that. We have at Orolia an Idm Protection Suite that's used to detect jamming or spoofing events. So if we detect something, we force the unit into holdover. That way we know that it can run in holdover and keep all of our timing requirements for some amount of time. We're going to use that backup rather than using the questionable GNSS. But in a more general way, the Department of Homeland Security has a whole resources page for this. I put the link there on the bottom, but it is a very good reference place to go when you're starting to learn about these things and investigate what type of solutions might be out there. You'll find 2 best practices documents there, and you'll find the PNT integrity library and an Epsilon algorithm suite. So 2 different things that can be integrated into existing solutions, either by the vendor or even by users, in order to perform this detection step. Right? And both of those are really focused on spoofing, but that protection step is really what we want to make sure, or that detection step, sorry. We want to make sure we can detect the event. So however we're doing it, it's important that we make sure we're looking into that, making sure that we'll be able to detect when something goes wrong. And then, of course, my favorite topic is about testing. So testing GNSS-based 5G devices. So this is a lot about the testing of that reference time clock. So if we have our reference time clock, we can test things with the simulator, like we can detect or create the threats with the simulation, and we can check our detection capability of the device. Does it detect, like I said, that 10 nanosecond per second time pull-off, or a variety of others that might be difficult for a receiver on its own to detect? We can check the holdover performance and ensure that we keep our timing accurate within the holdover time that we've planned for. So if we plan for it to take us through an entire day of outage, let's make sure that it really can do that. And let's check the response to interference and our response to spoofing. What actually happens in the system when we have these interference and when we have spoofing? So we can do all of that with GNSS simulation. So it's really important that even though you get a device that has a receiver, it's been tested, you want to know how it's going to react to these different conditions, because it's so important. And then at the bottom here, I mentioned Strike 3. So if you're not familiar with Strike 3, it was a 3-year project that ended in 2019, but what they did was they put different monitoring stations all over the globe, and they monitored for GNSS interference events. And then they characterized those waveforms into the most common. And after they did that, they released a draft report for receiver testing, saying here's the most commonly found interference signals, here's what they look like, and here's how to test for them. So that's one that you can use as a reference in what you should be testing. You can use it, with any GNSS simulator. The Strike 3 waveforms and scenarios, though, are available for our Orolia Skydel simulator. So if you're interested in that, we'll provide those for free. So you can just let us know, and we can get those waveforms and scenarios out to you so you can do this testing. And that's all I had for this topic today. So thank you, everyone. And with that, I'll turn it back over to you, Mackenzie.
Thanks, Lisa. For our second poll, the question is, for my precise timing needs, I require this accuracy. You have 15 seconds to answer. All right, and our results are interesting, a tie. All right, and with that, we will be hearing from Pierre Gerard, Senior Security Expert with Thales. Pierre, take it away.
Thank you, Mackenzie. So, hello, everybody. So we are talking here today about the 5G network, which will be a very big step in terms of generation compared to 4G, in terms of complexity, and also in terms of capability. But the question that always comes when talking about 5G is, what are the main use cases? What will be the killer app for 5G? So in fact, it's very hard to tell. I mean, I think who has the answer would be rich quickly, but it's very hard to tell. First, it was quite impossible to predict when we were designing the third generation of network, the usage that will be done on mobile phone, for example. So for this network, there is no reason that it will be the same. We don't really know what will happen on this network. However, I will talk about today about my field. So in Thales, we have a business line for automotive. So I will talk about what will be the application in the automotive industry for the 5G network. And I would like to say that the 5G network compared to the old generation has not been designed for with the consumer in mind. Okay, of course you will be able to have the newest iPhone which is 5G capable. Of course, it will be the network when it will be fully deployed will be quicker, so you will have, for example, higher definition video, but all the other features you won't be able to see them. So and it will be more useful for industries like automotive industries than for consumer, apart for the bandwidth, of course. Okay, so let's have a look of 5G in the context of automotive industry. So first, there are very different capabilities and very different aspects of this network. So sometimes you need all the newest aspects. Sometimes you just need one feature like broadband. And I will discuss these four aspects that you see there. So first, there is one aspect which is how the network itself is operated and how it's in fact built. Okay. A lot of new technology has been incorporated into the 5G network, like virtualization. So we talk about network virtualization function, software-defined network. So it's very new, and we will come back to that at the end when we will talk about security. But just for now, concerning the automotive industry is a full world where people like to have their own technologies. And just to give you an example, all the players in the automotive industry are connected to a network which is called ANX, Automotive Network Exchange, which is a fully private network around the globe. Okay, so just to give you an idea of how they are thinking, they just think in their own world. And here for the 5G network, they will, for example, an automotive manufacturer will be able to have what is called a slice in the network, which is just a sub-network, a private one, that is dedicated to just one customer or one usage. So a very large customer, like, I don't know, BMW, will be able to rent a slice of a mobile network just for its own usage, and it will be completely private. Concerning the second aspect, of course, there will be enhanced broadband, which will be very useful in the context of the automotive. For example, the video stream that could be collected from a car will be useful to create a detailed map, or to offer new services like collecting video stream from a car. Will be able to build a real-time cartography of what are the parking spots available in a town. Of course, this kind of application where you need real-time video streaming, you need really a huge bandwidth. Of course, later it will be used for autonomous cars. Okay, that will need detailed map that will be detailed, accurate down to the centimeter and in 3D. Okay, and this is a huge amount of data, so you cannot have that in the car all the time. So you will download it a little bit ahead of time. And that's for the download. For the upload, the autonomous car will generate a huge amount of data, really terabytes per hour of data that will be used for just logging and understanding how it works, and also for subsequent machine learning to reinforce the algorithm. So that's for the massive amount of data and broad bandwidth. There is another characteristic of 5G, which is called massive machine type communication, where you can have a density of things, connected things, which is really thousands and hundreds of thousands per cell, which is not achievable with the current technologies. Of course, for car, it's not useful, but for the automotive industry, it is. If you think about a factory, a car factory, highly automatized one, you have really thousands and thousands of things, of parts that will be put into the car, of tooling, of machine, of robots, that could be connected. And right now, the technology they have for wireless communication, like Wi-Fi, is not really good enough for their industry environment. And so now there are new factories built, like there is one in Germany built by Daimler, that connect everything in the factory with 5G. And like down to each screwdriver, it will be connected and track in real time into the factory. Okay, and of course it will allow really high density of connectivity, but also very low power consumption. Like if you have tools, you don't want them to have a big battery or to charge them very often. So the power consumption will be also very low. So that's for the massive IoT part. And finally, there is a part which is called ultra-reliable, low-latency communication. Okay, and this will be very useful once again for autonomous car that will need reliable communication. And here we are talking about really autonomous car, where there is no driver, even no steering wheel, where you need to be connected 100% of the time and to be reliably connected. And even if you have a problem with this car, someone will be able to take remotely control of the car and drive it back. Okay, and to do that, you need a very low latency. Otherwise, you will turn the steering wheel in the remote area, and then there will be too much time before the action takes on the car, and you will crash it. So, or you will have to drive very, very slowly, like you drive a rover on Mars because of the latency. Okay. So this is for the main characteristic of the network, and there is one additional one which is not quite well known, which is direct communication between the vehicle. Okay, so this is derived from an earlier technology from 4G and even 3G, which was called device-to-device communication. So this was not widely implemented, but it was a kind of push-to-talk communication where the communication does not go through a cell tower, but is going directly from a vehicle to a vehicle or from a vehicle to an infrastructure. So it allows to set up communication even when you are out of the cell coverage. Okay, if you are in the middle of nowhere, even if there is no cellular coverage, then you can still communicate between the vehicle and between the infrastructure and the vehicle. So what are the main use cases for that? Between the vehicle, it's mainly for anti-collision, so trying to avoid crash between vehicles. So for that, the car will broadcast their positioning and speed and acceleration 10 times per second. So with very accurate positioning and timing, so that the other vehicles are able to build a model of the surrounding and detect if there is a collision course. And between the cars and the infrastructure, you have use cases like signal phase and timing, so the traffic light will communicate to the vehicle when they will turn green or red, so that you can adjust your speed. Or you can broadcast things that like ongoing traffic jam or accident ahead or things like this. And of course, you will have also communication with the pedestrian that will also have 5G device in their pocket, okay, to avoid collision or accident with a pedestrian. And finally, there is one link that is possible, which is the classical one, the link that you know, which is the cellular one. So here you see it with a satellite because 5G will integrate satellite, but you can also communicate with the classical cellular network for, I don't know, the classic services you have on your dashboard today. Of course, offering all those new services, this new complex network is a challenge in terms of security, and this is what Thales is working on. So we are working on car automotive security, and of course, within that area, on 5G security as well. So as the network is much more complex, integrating a lot of different building blocks that are often virtualized, security is very important and key in this new complex network. So the first point is to have authentication between all the elements of the network, mutual authentication. So of course, you all know the SIM card that you had in your mobile phone, which is meant to authenticate the user to the network. But all the different elements of the network will integrate such kind of secure elements. So it could be the equivalent of a SIM, which is soldered, I don't know, inside the antenna, base station, or it could be a bigger SIM card, which is called HSM, Hardware Security Module, which is a rackable big smart card that is able to store key, perform cryptographic operation, so that the different elements of the network could authenticate one another. And once you have this authentication, you can deploy other security functions like encryption to protect data that we call at rest. Okay, when you have a server or database, you can encrypt and protect them in terms of integrity, and you can also protect the data when it's moving across the network, okay, so when it's in motion, and then you can encrypt once again and protect the integrity of the data that is moving across the network. Finally, in this complex environment, it's good to design the security, but it's also better to test it. So we provide, for example, in this area, services like penetration testing or consulting services to design and not only test from time to time with penetration testing, but also to constantly detect problem and make some evolution on the network to correct them. So like we can monitor in real time if and detect ongoing attack and react to those attacks. Okay, so sorry for the. So to conclude, 5G is a very complex and new network offering many different capabilities. Depending on your area, you don't need all of them. For the automotive industry, most of them will be used. It's, of course, an opportunity, but it's also a risk in terms of security. So we are working to protect them, and it will be a challenge for the years ahead. Okay, that's all for today. So back to you, Mackenzie.
Thank you so much. That was great. For our last poll, the question is, if a GPS weather reporting service was available, what would you do? You have 15 seconds to answer. Interesting. All right. Now we will hear from Cecil Taylor, Senior Product Manager for Anritsu Company. Cecil, after you.
Okay, thank you, Mackenzie, and thank you everyone for being here today. I'm going to focus on reliability, performance, and safety of mobile operator networks, really primarily in terms of enhanced mobile broadband, like Pierre was talking about, and I intend to fulfill the part of the webinar devoted to consistent operations during signal loss. So to give you an overview, I want to get into how mobile operators use simulated 5G AGPS testing to achieve consistent operations and reliability and performance and safety. But first I want to start with how they generally use simulated testing and why, and then we'll move on to the specifics of AGPS testing and wrap up with a brief look at the future. So the way mobile operators test devices on their networks, they have multiple options. First is field testing using a live network. This has its difficulties, though, as we'll see. An interoperability lab where they bring network equipment and devices together and just try it all together. But what's really popular is also simulated environments, either using standard or carrier-specific testing. Now, there are different groups that offer standard testing or definition of tests that people can use. GCF and PTCRB are two of the big ones in our industry, but there's a slew of others, some of which are shown here. What I want to focus more on is on carrier-specific or carrier acceptance testing in this particular presentation. So why do mobile operators use carrier acceptance testing? Well, especially because it's very expensive to run a CAT program and coordinate an operator's testing ecosystem of chipsets, devices, and test houses. One operator vice president once told me he is always trying to kill the carrier acceptance program due to expense, but the benefits outweigh the expense. And you typically see CAT programs in very competitive markets where customers have options and aren't afraid to use them. So the first reason is switching risk as a result. Customer perception often when a phone goes haywire is that it's a network issue, so they complain to the carrier. And also, if you think about it, it's less difficult for them to switch carriers than maybe to switch out their phone. So it falls on the carrier to have the quality of the network and ensure the devices have quality. Lower support costs. It's really difficult to reproduce field problems. I was in a role before. I used to sell to operator support teams that track down problems, and it is like finding a needle in a haystack on a live network to know what really happened, what really went wrong. So it's very difficult, very costly. Operators want to avoid that if possible. Customer satisfaction can attract new customers because people compare. They talk about their phones, they talk about their networks and how their phones perform on those networks. And so high satisfaction can attract new customers in competitive markets. And then confident branding of devices. Usually network operators will have devices that they sell through their stores. In the U.S., it's the primary way that people buy phones, actually. So they want to have confidence in the performance of those special devices on their networks. Now, the devices actually don't like to have to do extra work for the carriers, but there are some benefits that they accrue from it. One is they're allowed to use the mobile on the network. It's a requirement that they go through this. So unless they get some special waiver, they have to do it. They also have the branding opportunity. If they want to work closely with the carrier and they want to sell through their stores, then they want to go through the more rigorous testing. And they also have higher quality and lower support costs as a result. I want to talk now about how carriers have different philosophies for what to test in their simulator testing. Some will mainly use standards-based testing, but then they'll add some cases that are unique to their particular network, maybe the particular frequencies they use. Some focus on problem areas. They're expert enough, veteran enough, that they know where the problem areas are with devices in their network, and they craft tests that are focused only on those problem areas. Some problems are difficult to reproduce, so these carriers usually find problems in the field or interop lab, but then they bring them back in to the simulator environment to try to reproduce them and have tests for those. And then some carriers actually test the total network requirements. They don't use standards testing so much. They will use the field and interop testing, but they want to simulate everything in the lab before it goes out the door. So how do network simulators work? Well, if you take, for example, our Anritsu 7834NR system for 5G, it's very similar to other simulators in the market, that it has a layered approach that loosely matches the network layers. So handling the RF protocol and core network layers with then test scripts running atop the simulation. Now, there's a big difference between simulator and live networks because the live network wants to work perfectly. In the simulator, as we're simulating the network to the device, we want the ability to create errors. We need specialized equipment to do that. We need a way to manipulate signals down at a micro level to create the conditions to where we know that a device that goes out can recover on a network. This is part of the reliability and performance I mentioned earlier to ensure consistent operation. Now, we can create errors and disruptions not only at the RF layer, but also in the protocol layers. At the network layer, core network layer, we typically do just enough to simulate everything. Maybe we don't implement all of IMS, just enough of the stack to enable the tests. So anything kind of the core network layer tends to be a little lighter in its weight. Also, data traffic, instead of a high variety of different kinds of data traffic, most of the time we'll use CAN data rather than variable data. I know a lot of people on here are very familiar with satellite. I know some of you are not. So I wanted to mention just for a moment, what is a GPS? What is assisted GPS? And of course, these kinds of things also apply to other global navigation satellite systems, but I'm I'll always be using GPS as the example. So in GPS, satellites send a detailed report of their position and parameters to help predict and correct the satellite position and where the phones know that they are, so the device can determine the position based on the signal time traveled and trilateration from multiple satellites. Now the problem is this time to first fix is done at lower bit rates and can take up to 20 minutes to determine the position of a mobile phone. So in assisted GPS, one or more elements in the network monitor the satellites continuously, and then the same satellite position and parameters are forwarded to the phone from the network, just as the satellite would send. So over a cell network, this happens in a few milliseconds. And as a result, the device can lock onto its position, that time to first fix, in a few seconds versus several minutes. So the way this is implemented in the simulator world, I'll use the Anritsu Orolia partnership as an example, as we're working together to provide this kind of simulation for AGPS. So Orolia has a specialized solution for Anritsu to be able to fulfill the needs of carrier acceptance testing. It's called the Orolia GSG Sky ANR. And so this will simulate the GPS signals that are going to the mobile, done in a lab environment, connected directly to the device. Now, the satellite dish in this picture is replaced with a direct connection between the GSG Sky ANR and the Anritsu ME7834NR to pass that satellite positioning data, and then Anritsu delivers the positioning information through its simulated network layers to the mobile. So Orolia handles the satellite part, Anritsu handles the cellular part. So why do mobile operators that use simulated testing, why do they do it for AGPS? Well, there's four main reasons that I'll cover: repeatability, debugging, in-building limitations, and special scenarios. So for repeatability, there are so many variables in the field or where you have multiple components in an interop lab, and you want to isolate to the device rather than all the variability in network conditions or network components, because otherwise you don't know what's right, what's wrong, so you just want to know if the device is working properly. In AGPS, in the real world, satellites are moving, so they give different data every millisecond. Simulators use CAN data and CAN sequences to create the same conditions. Now, of course, you have cases like weather, trees, urban canyons. Can't change the weather in the real world, but with simulators, you can vary power levels or set up missing satellites. In the real world, there may be 11 satellites in the field of view, but you could increase or reduce those numbers with the simulator. This is the case in urban canyons, where satellite paths may be blocked, or you may see too many false satellites due to reflections. Lisa talked about this a little bit in her presentation. As simulators can perform controlled multi-path scenarios to simulate building bounce. Very similar is to use simulation for debugging. It's a controlled environment. You can isolate the device under test. You can eliminate other variables. There's repeatability, which is so important in debugging. The best simulators are able to reproduce the test accurately time after time, and that's something Anritsu actually is known for. If there is variability, it's costly and time-consuming to reproduce, so that's why you don't want to use a field setting. And then once a field scenario is understood, most operators prefer to represent it with a test that will prevent future occurrences in the forthcoming devices. Next are in-building scenarios. A problem with GPS positioning is in-building use. You can't always achieve accuracy. You might even have to go outside your own building to do your testing. So in a cellular network, you can fall back on other techniques. Today, there are things like enhanced cell IDs, observed time difference of arrival, things like that. And there's new technology coming to also assist, such as AOA or angle of arrival in 5G. Operators also face some new requirements for not only horizontal location, but vertical location or altitude, which are important in multi-storied buildings. And you need simulators to test those kinds of cases also. Imagine going up and down elevators during the day to find a particular barometric pressure. You want to be able to simulate that and have efficient testing. And then the fourth case for simulation is in AGPS is special scenarios. You have field concerns. Of course, we heard Pierre talk about some of this. There's quality of networks as mobiles roam globally, and security may vary in different network settings, and there's different components of security. Mobiles can be vulnerable to jamming, spoofing, other kinds of interference. And by the way, the Orolia GSG Sky ANR helps us address such scenarios. And simulators can create their own jammers as well. So for an example, U.S. operators want to ensure that a device roaming in China does not attach to a Wi-Fi signal because more vulnerabilities can occur there. So the operator may not allow the mobile to make Wi-Fi phone calls while in China, and they can send messages or monitor to make sure that the mobile is not doing that. And we can simulate that whole location scenario without actually having to take a phone to China. Finally, I want to talk about some of the future apps and use cases as positioning usage is growing, and both real networks and simulators must keep evolving. Right now, there are things like wireless emergency alert, being able to broadcast alerts to mobile users. This is paired with geofencing, which is broadcasting within a perimeter or boundary. So mobile game apps may use this. Another example, in the U.S., there are Amber alerts for missing children. So those are only broadcast within the range where the perpetrator might be expected. And then vehicle synchronization and tracking. Pierre talked about this a lot, and there's also fleet tracking as well. There was a case in Europe where truck drivers were actually fired from their company due to inaccurate data of how the fleet was managed and where they were traveling. It would show, their system would show that the driver had stopped for 4 hours and then drove at 90 miles per hour or 145 kilometers per hour to arrive at another location. But in reality, they were driving more steadily the whole time. So this is something where you need a good application to understand that. And there may be more and more applications being built atop GNSS. And actually, this is where I want to conclude my presentation, is talking about the way that positioning technology is evolving. I was talking with our positioning lead in Anritsu, and we were remembering the start of wireless data, how we were just focused on how to get data through a phone, and never really imagined social networks, streaming video, etc. Positioning technology is poised to have the same kind of unpredictable explosion of applications. And at Anritsu and in partnering with Orolia, we can help build and test the infrastructure for those applications to come. So with that, I conclude my presentation, and Mackenzie, I'll hand it back to you.
Thank you all. That was amazing. At this time, we are going to jump into some questions we received during registration and a couple that we got during the live presentation. The first one is actually for Cecil. How are advancements to take full advantage of 5G?
Well, 5G is rolling out, and certainly within the U.S., you're seeing some heavy promotion of 5G. But to really advance it and fulfill the full vision of 5G, I think there's a couple of key things that have to happen. One we really haven't talked about on this call is the shift to millimeter wave. So currently carriers are using lower frequency channels to create an evolution of 5G, but the revolution will happen when you go to this higher frequency millimeter wave. And it's a very complex technology. It really has a long way to go. Even though it's deployed in pieces, it has a long ways to go before it's widely deployed and very confidently deployed. And then the second thing is, actually Pierre mentioned this 5G network of networks, and one of the things in there was the massive IoT with the Internet of Things. And it's not nearly what it's going to be. And Pierre mentioned this, that you have network slicing, being able to separate network traffic according to purpose. So with massive IoT, a lot of the devices don't need much bandwidth, but they can flood the network with its density because they're always waking up, maybe transmitting some small amount of data, going back to sleep. You can imagine, he talked about the screwdriver in the factory. There's a little bit of data that may be sent all the time. So you have to imagine a tremendous number of very small messages flowing through the network all the time. So network slicing will help manage this. We're starting to talk to operators about that right now. They're doing some initial experiments with it, and I think by next year you'll start to see network slicing deployed. you combine these two things of millimeter wave and the massive IoT, I still think we're about 3 to 5 years away from really seeing 5G be what it can be.
Gotcha. My next question is for Pierre. How does high-speed broadband internet from satellite Starlink compare to 5G services?
The comparison is a little bit difficult for various reasons because so first, 5G will be also available via satellite, even if it's not the case today, but it will. So it's under synchronization. So, but let's suppose we are talking just about terrestrial 5G here. So, on top of that, Starlink is a proprietary technology from SpaceX, so there is not a lot of data available. And 5G is, as we have discussed today, is really a multi-faceted technology. So it all depends about which aspect you are interested in 5G. So if you are talking about massive machine type communication, you are not interested about the bandwidth, but more about the low power consumption or low signaling traffic. But okay, so let's talk also about just enhanced multimedia broadband. So first, Starlink is a fixed technology, whereas 5G is at the beginning a mobile technology. Starlink, so SpaceX has announced also mobile version of their terminal, which are really bulk one currently, but we don't know. So we'll see in the future. All in all, concerning bandwidth, Starlink provides less bandwidth than 5G. Okay, although it's already a comfortable one. We are talking about gigabyte per second, so which is quite good. But we don't know about the scalability. Okay, so right now they only have a few thousand of users. So the feedback is good. They have more or less their gigabyte per second. But we'll see how they will be able to scale up. Okay. Whereas 5G is redesigned for massive amount of device, a massive density in a cell. So the good point now, Starlink is a global coverage by definition, so they are a global satellite system, whereas 5G coverage is quite limited to highly populated area due to the fact that to have really this large bandwidth, you are using shorter wavelengths, so higher frequencies. So the coverage of one cell is really small, so you need to put a lot of them. So it's fine in populated area, but outside the cities it's not that good. So that's why 5G will also put the satellite link later on. So all in all, I think that they will add what is missing on one side and another, but ultimately Starlink will remain a proprietary technology. Whereas you have 5G as really open ecosystem with hundreds of companies, hundreds of partners working on it. So that's what I can say today about both technology.
Great. All right, my next question is for Lisa. What are the biggest PNT resiliency challenges for 5G?
Yeah, I think that the biggest challenge, just like it is for everywhere, is first awareness. Just that GNSS devices are vulnerable. So that is a big problem that a lot of people just make an assumption that, oh, it's on GPS, it's going to work. They're not aware of the vulnerabilities. So just getting that awareness out there. And then this next biggest hurdle will be cost. So there's a lot of technologies out there, but a lot of them are paid. We don't see that people are really just jumping on the paid services. They're either not informed or not willing to pay for that level of protection. So it's just about getting the awareness out there so people see the value in updating their legacy solutions, or when they're choosing something new, that they're actually looking at the resiliency ratings of the device and understanding how it works in order to see what other outside of that device protections might be needed.
Okay, great. My next question is for Cecil. Are 5G operations synchronized to GPS? Is it network-wide, a mandate, or just an option at the network operator's discretion?
I would say it's definitely a mandate. Well, I mean, there's business cases like I showed before, but definitely a mandate. There's regulatory bodies that have requirements that drive the solution. So it doesn't necessarily have to be a GPS solution, but they need a solution to fulfill the mandate. So I'm more familiar with the U.S. requirements. In recent years, networks have had to assure 50-meter horizontal location accuracy for 40% of their network E911 calls. And just last month, that got raised to 80% from 40% to be within 50-meter accuracy. Now, there is a loophole on this that you have to be deploying, the operator has to be deploying voice over LTE or voice over NR technology. And for 5G, this VoNR technology is something we're working on right now in the lab. It's just being deployed in some trial markets. So the U.S. operators are probably 1 to 2 years away from having to fulfill this legality on 5G. Now, what's interesting is in that change last month, for the first time, U.S. operators had to also do the vertical location accuracy I was talking about in my presentation. So you can either do that with the vertical location techniques like barometric pressure that I was describing earlier, and with those you have to get within 3 meters of altitude 80% of the time on the wireless E911 calls. But they do provide for an option that if dispatchers can identify the location vertically from a message from the phone, such as room number or floor number on 25% of the calls, that's okay too. So I would say it's a mandate. It's because of what the requirement is, and it's happening, and we're going to see a lot of advancements in the next couple of years for E911.
Great. We have time for one more question. This one is for Pierre. How can one simulate different types of attacks?
So the first thing to know is that you cannot simulate all of them. So it's really a very hard task to think in advance of which kind of attack will be devised by hackers. So of course you can simulate some of them, and we have been presented that. Now there are some advanced techniques to simulate attacks in a more evolved way, let's say. So first you can be helped by artificial intelligence, where you can train system to generate attack by learning on existing attack, an existing set of attack, and then you can produce after that a lot more attack from the AI engine. That's one way to, let's say, extend the range of simulation. Another one is to use human intelligence, which is so far in this area far better than artificial intelligence, because you have the creativity of the human that can come up with something completely new that nobody was aware of or have thought about before. So that's my take of that.
Great. Okay. All right. Thank you for attending today's webinar, Resilient PNT for a 5G World, brought to you by GPS World Magazine and our sponsor of the event, Orolia. If you have any additional questions for myself or for our speakers, you can reach out to us directly via the email addresses you see currently on the slide. The resources panel houses a PDF of today's presentation slides, which you can download. To access this panel, if it is not currently visible, click the green icon at the far right end of the toolbar at the bottom of your screen. A recording of this webinar will be emailed to you tomorrow and posted to gpsworld.com/webinars. Upcoming webinars from GPS World will also be posted to that page. Thank you all for attending, and we hope you'll join us for another great webinar.